Hello, and welcome to this quick take video, where you will learn about Vivato's new ReportCDC command. This command was introduced in 2014.3, and GUI support was added in 2015.1. In this video, we will review what synchronous and asynchronous clocks are, and which of these require special attention for clock domain crossings. Throughout this video, I'll be using the terms clock domain crossing and CDCs interchangeably. Next, I'll briefly remind you of the issues that can occur at CDCs and review some of our recommended best practices. Then I'll give you an overview of the ReportCDC command and some of the topologies added for 2015.1. Finally, I'll launch Vivato and show you how to use the command, debug, and fix CDC issues. The relationship between clocks is very important for a timing tool to understand. In the top diagram, you can see a primary input clock driving an MMCM clock generator. Out of the MMCM are two generated clocks that launch and receive the data across the CDC. In this case, the timing engine has complete visibility as to the relationship between the frequency and the phase of the two clocks. These clocks are synchronous, and the timer will calculate the worst-case relationship that can occur between the two clock edges to correctly time the setup and the hold paths. From a CDC perspective, these clocks are safe, since the timing tool can truthfully report the timing. Do not confuse a safe CDC with a design passing timing. Safe only implies that the timing engine can properly time the path. In the bottom picture, the clocks that launch and receive the data across the CDC are primary inputs. Even if the user specifies the frequency of these two clocks, the timer cannot infer any edge relationships between the two clocks. In the absence of any other constraints, the timer must assume that the two clocks are not related and time them asynchronously. ReportCDC will show these paths as unknown unless they match a known safe topology. You are responsible for reviewing all asynchronous clock crossings that exist in your design and ensure that they function properly. Let's quickly review the main problems that arise at CDCs. Let's assume that clock 1A and clock 3A are not related. Output data from flop FD4A will transition shortly after clock 3A's rising edge. This transition may violate the setup or hold time of the flop FD11A. The output of FD11A can become metastable and will require some amount of time to resolve to a legal, logical value. If I add another flop in the receiving clock domain, as long as the time it takes for the X to resolve itself to a correct logical value is less than the clock period of the receiving clock, then flop 12A is guaranteed to never become metastable. The synchronization circuit will ensure that the metastable data is never propagated through the design. But the design itself must be tolerant for the variable latency required to cross the CDC. That's an entirely different quick take video. With that in mind, here are a few recommended best practices for CDCs. First, limit the number of control signals that cross the clock domains. For example, consider combining a load and an enable signal into a load enable rather than using separate signals. As with most things, fewer is always better. Less things to verify, and in general, a more robust solution. For synchronized-based CDC circuits, use a 2 or more stage synchronizer and always include the asynchronous reg property on every stage of the synchronizer. This constraint will drive the placer in the router to improve the robustness of the circuit. Thirdly, if you use asynchronous resets, synchronize them. The advantage is that upon deassertion of the reset, the state of the design is known. Finally, use gray-coded pointers for FIFOs, or if you need to synchronize many control signals. Gray-coding the signals will enable you to detect when all the bits have properly transferred between the clock domains. ReportCDC detects structural issues in your design. It compares your gate-level netlist against known safe CDC crossings. For the report to work correctly, you must ensure that all clocks are defined and there are no unconstrained clocks in the design. The command will report structural issues on all paths between asynchronous clocks and on all user-ignored paths between synchronous clocks. Paths are user-ignored when clock groups or false paths or set max delay data path only constraints are specified. The command will issue a severity of critical or warning if structural issues are detected. A warning severity is also issued in the case of missing asynchronous reg properties. An info severity is issued if the CDC path is safe and an asynchronous reg property has been properly set. Vivado 2015.1 now supports 16 CDC structures. The 4 shown here are new in 2015.1. CDC H10 will detect if you have any logic between your synchronizer. CDC H11 will detect if you have any fan-out between the launching domain and the receiving domain. We also detect if multiple clocks fan into a synchronizer. All of these topologies could result in errors in your design. With future releases of Vivado, we will continue to grow this library of topologies. Let me start Vivado and show you a brief demo. Here I have a simple design that has already been synthesized. Let's go ahead and open the synthesized design. ReportCDC is only available post-synthesis, since it finds topologies in your gate-level netlist. To run ReportCDC, under Tools, choose Timing, and then ReportCDC. The dialog allows you to change a bunch of settings. You can limit the results to a particular clock domain, and choose output files to write your results to, among other things. For this demo, we'll just leave the defaults and click OK. Looking at the categories on the left-hand side of the report, there's a summary by clock pair, a summary by type, and a section for each clock pair. By default, you are placed in the summary by clock pair table. This table allows you to see the severity of your CDCs by clock pair. Let me quickly mention each column. The first is severity. Obviously, you want to especially pay attention to anything listed as critical or warning. Then we have the source clock and the destination clock, followed by the CDC type. This design does not contain all the types, but you can see a few listed here. The exception column shows you if you have any existing XTC constraints between the two clocks. Set max delay data path only tells the engine to ignore clock skew and jitter and keep the clock to queue plus logic delay below a target value. Asynchronous clock groups are user constraints that tell the engine that there is no edge relationship between the two clocks. Endpoints specify the number of path endpoints that exist between the two clock domains. The safe column will list the number of endpoints that are synchronized or match a known safe topology. The unknown column indicates the number of endpoints that ReportCDC cannot determine if they are safe. These should be looked at closely and may either need to be fixed or convince yourself that they are correct. Finally, the last column indicates how many synchronized signals are missing the asynchronous reg property. These constraints should be added prior to implementation so that they are correctly placed and routed. Let's take a look at the two critical unknown endpoints between clock 166 and the divided clock. If we click on the number 2 link, we are taken to the clock pair page, and the category filter has been changed to unknown. I can click on the violation and either click the schematic button or press F4 to open the schematic. This is basically showing you the exact CDC. In this case, the driving flop is on the clock 166 and the receiving flop is on the divided clock. If we expand the clock networks of these flops, we'll be able to see this. You can do this by double-clicking on each of the clock inputs. If I also click on the Q pin of the flop in the receiving clock domain, you can see that this is an unsafe clock domain crossing and would need to be addressed in the RTL. To find where the CDC is in the RTL, you can select a flop, right-click and choose Go to Source, or press the F7 key. Here's where you'd need to modify the code to add a synchronizer. Making a few edits will solve this problem. I have this set up already such that I can uncomment a few lines and I can add the synchronizer. I'll go ahead and save the RTL. You'll notice that the synthesized design goes out of date. Let's look at the remaining issues before we resynthesize the design. For the paths between sysclock and clock 83, it looks like we have 9 endpoints, and all 9 are synchronized. But it looks like we're missing the asynchronous reg property on the synchronizer registers. Let's go ahead and confirm this. We can click 9 under the No Asynchronous Reg link, and we'll be put onto the clock-to-clock pair section with the category filter set to No Asynchronous Reg. Selecting the line and clicking the schematic button, I can see the CDC. I'll expand the schematic a bit so we can see the synchronizer. It looks like all we need to do is add the asynchronous reg property on the FD1A and B cells in the mul_add2 sync 0 level of hierarchy. Clicking back to the summary by clock pair, we can do the same for the sysclock to clock out MMCM clocks. I'll click on the 9, select the line, and hit F4. It looks like we have a second instance of the sync 0 instance. Let's go ahead and add the asynchronous reg property. This is probably easiest via Tickle. Clicking over to the Tickle console, we can first get all the cells. I think if we get all the cells that exist in the sync 0 level of hierarchy that start with the FD, we should be good. If we use the hierarchical option with the get cells, we should be able to get all of them. I think this is correct, but let's check how many cells we'll be adding the property to, just to be sure. I can use the L length to get the length of the array. There are 36 cells, and that makes sense. 2 per synchronizer, 9 bits, and 2 instances. Let's go ahead and set the asynchronous reg property on these registers. We can check this by selecting a register and seeing if the property is set. It is. By doing this, we've added a constraint to our XDC. Let's go ahead and hit the Save button. Now that we have addressed all the errors, let's go ahead and rerun synthesis. We'll go ahead and reopen the synthesized design. And rerun ReportCDC. As you can see, everything in the design is now safe, and we are confident that all the asynchronous reg properties are set. This design is ready for implementation. As you can see, ReportCDC identified all of the issues and enabled us to cross-probe to the schematics and the RTL to quickly resolve them. To summarize, this quick take video outlined the ReportCDC command in the Vivado 2015.1 release. ReportCDC allows you to quickly identify complex CDC issues early in the design cycle versus trying to fix them in hardware. In 2015.1, GUI support has been added, which makes debugging easier with cross-probing to both the schematics and the RTL. This tool identifies 16 CDC structures and reports safe and unknown CDC topologies with either safe, warning, or critical severities. In future releases, we'll continue to grow this database. I hope you found this quick take video useful. If you'd like to get more information about Xilinx, follow us on Facebook, Twitter, or subscribe to our YouTube channel. Thank you very much.